In this video, I'll introduce neural coreference resolution models. I'll provide an overview of the concept and cover some key equations before going through what a sample neural coreference resolution model might look like. So far in this module, we've focused heavily on feature-based coreference resolution models, where we determine some optimal feature set, extract those features from labeled training instances, and then learn to predict probabilities associated with candidate co-referring expressions using standard machine learning algorithms. However, recently there has also been significant interest in neural coreference resolution models. Neural coreference resolution models work a little bit differently from the other models we've seen so far. They're generally end-to-end systems, so you feed in raw text as input and directly end up with scored pairs of anaphors and their antecedents as output, rather than having separate steps for mention detection and mention clustering. Behind the scenes, this means that a neural coreference resolution system typically works as follows. First, the model will consider every possible span of text as a mention. So we'll consider two spans, I and j, of arbitrary length less than some value k. The model will compute three values based on those two spans. M of I will determine whether span I is a mention, M of j will determine whether span j is a mention, and C of I and j will determine whether j is an antecedent of I. The model will then assign a score to I and j based on the combination of those three values. The functions m and c are computed using feed-forward neural networks that accept vector representations of I and j as input, and these vector representations might contain word embeddings, manually defined features, or some combination of the two. A sample neural coreference resolution model then might look something like this. Let's say we start with an input sequence of text, so this could just be any sequence of text, like UIC says it's handing out free face masks or something like that. We find a vector representation for each word in the input sequence, so these vectors, as already mentioned, might contain word embeddings, manually defined features, or some combination of the two. We encode the input sequence using a neural model of our choice. This might be something like a bidirectional LSTM. We end up with an encoded hidden representation for each possible span of text. So we take a given span representation and pass it into the two different feed-forward neural networks that we already mentioned. One determines whether the span is a mention, and the other determines whether some other span j is an antecedent of the current span. So we end up with mention scores and antecedent scores resulting from those two networks, and we sum them along with the mention score for j, which would have been computed at a different time step to compute our coreference score. Then finally, we apply a softmax function to all of the coreference scores computed for the input sequence to end up with our final set of coreference chains.